All right, well, welcome everyone. It is my pleasure and honor to introduce the afternoon's session. And this session is dedicated towards characterizing, sampling dynamic systems. And we'll explore this from several different perspectives, whether you're in the canyons and mapping the deep sea, or in the atmosphere, terrestrial interface around volcanic systems, or in the upper several hundred meters of the ocean. All of these environments present a challenge in how we access, sample them, characterize them spatially and temporally. And so I think what we'll see is that there are some commonalities from a fundamental technological perspective, but also the challenge of data and how we incorporate the data, synthesize, present an integrated view of the system. And so without further ado, I'm going to introduce our first speaker, Dr. Veerle Huvenne, who comes from National Oceanographic Center in Southampton. She received her PhD from the University of Ghent. And I'll spare you all of the details for all of these distinguished speakers and direct you to your program where you can read more about them and in deference to them to give them the most time to present their work. So without further ado, Dr. Huvenne.
Thank you very much, Chris. Good afternoon, ladies and gentlemen. This presentation will be very much taken from the point of view of a science user of these autonomous and robotic vehicles rather than a technological developer. So from that point of view, I am more like an early adopter rather than an innovator, referring to Gwyn's classification. Before I dive into the presentation, I would like to thank the organizers of this conference for the opportunity to present some of the latest developments in the study of complex deep sea environments. And if we're talking complex deep sea environments, submarine canyons certainly tick the box. The latest estimates indicate that there are about 10,000 medium to large scale submarine canyons around the world, and plenty more small scale ones, of which most of them are even not mapped yet. Submarine canyons are the main transport pathway between the shelf and the deep sea, funneling large quantities of sediment in sometimes very catastrophic flows, but equally in an accumulation of small-scale processes such as repeated rock falls or the repeated resuspension of seabed sediment through internal waves and currents that get focused in the canyon. Unfortunately, together with that sediment transport, also a lot of anthropogenic litter and pollutants make their way to the deep sea that way. The fact that submarine canyons create such an incision in the continental margin also mean that they have a strong influence on the oceanography, on oceanographic patterns and current systems, creating features such as upwelling, focused internal waves, eddies at the surface, or also more interesting phenomena such as the largest surfed wave offshore Nazare, which is brought there through the funneling action of the Nazare Canyon. Those processes also create quite often an enhanced surface productivity, which then cascades down through the food chain, both at the surface and down to the seafloor through bentopelagic coupling. So, as a result of this multitude of processes and the very heterogeneous terrain that submarine canyons present, they're also very often hotspots for biodiversity, and this ranges from typical sediment dwellers over substrate-specific filter feeders, such as these submarine canyon, coldwater corals, and all the way up the food chain through fish up to top predators such as swordfish or cetaceans. And this richness doesn't go unnoticed. Submarine canyons are often rich fishing grounds, attracting fisheries using long lining techniques, bottom trawling, and such more, which can actually have quite severe impacts on the seabed, including mechanical impacts, as you can see there, or the creation of large smothering sediment plumes, or the creation of ghost fishing through lost fishing gear. So policymakers and governments now have the task and the responsibility, but also the problem to decide which areas of submarine canyons to protect, which areas to set aside for fishing. And to answer that question, they need to know which parts of submarine canyons host the highest biodiversity, where can they find specific protected species, where can they find vulnerable marine ecosystems? And to help answer those questions, a team of 28 scientists and engineers set sail on the 9th of August last year from Southampton on board the RRS James Cook for a 5-week expedition in the Whittard Canyon. Whittard Canyon is the largest submarine canyon on the Celtic margin in the Bay of Biscay. It's about 200 kilometers long, has 4 different main branches, reaches from 200 down to more than 4,000 meter water depth. And this expedition was part of the CodeMap project, funded by the European Research Council. The aims of CodeMap are to develop a robust, integrated, and fully 3-dimensional methodology to map complex deep-sea habitats, to quantify habitat heterogeneity, and then to test the potential of that habitat heterogeneity indicator as a proxy for biodiversity. But submarine canyons are not very easy environments to work in. They cover a vast area, as I said, Whittard Canyon, 200 kilometers. They host sometimes very steep terrain, as you can see up there, going to vertical or even overhanging cliffs. They're also home to pretty strong currents in some locations, which do not only pose a risk for the equipment that we put down in the canyon, but also can create a very high turbidity, which then limits the visibility when you use any photographic or video equipment. They cover a large depth range, so any equipment that we put down ideally needs to be able to deal with that depth range. And as I said, they're very heterogeneous. There is a high variability at very fine spatial scales. And to really understand the submarine canyon and how it works and where the species live, we need to be able to capture that and understand that variability and know how to work with it. You kind of can compare it, to visualize it a bit, as if you would try to make a detailed biodiversity map of the entire Grand Canyon, but you're working from a hot air balloon on a cloudy day. And traditionally, people could only occasionally drop a piece of equipment down to the seabed, such as a camera or a corer or another sampling equipment. So this is kind of the environment or the challenge we are set. And in terms of specific requirements, so for our CodeMap cruise last summer, we wanted to set in place a methodology that allows us to observe and quantify the seafloor and its communities, covering all scales and depth ranges at the necessary resolution, including surveying under overhangs or along very steep canyon walls, including a characterization of the water column and the hydrodynamic regime. And then the next step is to integrate all of that into a comprehensive visualization, ideally in 3D. And finally, there were also challenges in terms of integration, those different resolutions, those different data types, navigation and positioning, which has already been mentioned, and I'll come back to that in a minute. So to answer the first challenge, to cover all the scales and depth ranges at sufficient resolution, we made use of a fleet of vehicles. And next to the RRS Discovery, the sister ship of the James Cook, you can see the fleet of the MARS facilities, the Marine Autonomous Robotics Systems facilities at NOC. And although it's a pity that those vehicles at that moment weren't in the water and actually collecting any data, it's fantastic because this way I can demonstrate all the vehicles we have and which ones we used. And so for the cruise last summer, we made use of the AutoSub 6000 in the center there, the ISIS ROV, and a sea glider similar to the one here at the bottom left. Our expedition was actually the very first for UK science to deploy an AUV, ROV, and a glider simultaneously in the same research area. And on top of that, we chose a deep sea canyon as a complex deep sea environment. However, at the same time, while we were out working in the Whittard Canyon, colleagues of us from 2 different projects were also working on the Celtic Shelf, and were deploying additional equipment, including the AutoSub 3, more gliders, and some of the unmanned surface vehicles. So altogether, this demonstrates how we are moving towards a system where we are trying to obtain a holistic picture of an entire system, covering the Celtic shelf, the margin, including the processes happening in the canyon. And we are using a combination of vehicles and tools that let us capture every detail and every process in the right resolution as we go along. So to just introduce the vehicles a bit more, we used AutoSub 6000 AUV, as I said. It's 6,000 meter depth rated, and we mainly used it for acoustic mapping. So we had an EM 2040 multibeam echo sounder system on the vehicle that allowed us to map the seafloor down to a pixel size of about 1 meter. We also have an EdgeTech dual frequency side-scan sonar, which allows mapping at finer resolution. However, it doesn't give any topography. AutoSub 6000 can also carry out photographic missions. However, for that, it needs to fly at about 3 meters above the seabed, between 3 and 4, ideally, which in a submarine canyon is not trivial. Most of AutoSub's missions were around the 24 to 28 hour mark. We then also used the ROV ISIS. That was more for precision sampling, high definition video, high resolution photography. But ISIS also has a Reason 7125 multibeam system, which we use to do bathymetric mapping at ultra high resolution of specific features that we have an interest in. And then, as I said, at the same time, we had the Sea Glider from the University of East Anglia in the water for a 21 days continuous mission, carrying out about 10 profiles of the water column per day, down to 1,000 meter water depth, measuring temperature, salinity, oxygen, and turbidity. So using that fleet of vehicles, as I just described, this is an example of how we then tackle this question of covering all scales and depth ranges. We develop a methodology of carrying out nested mapping, so zooming in at increasing detail. And so in the background you see bathymetry collected with the ship, 2 different surveys there for 2 different color schemes, pixel size of around 25 meters. Nested in there is the AUV bathymetry, pixel size around a meter, and you can see already some of the detail in some of the gullies in the southern end. Zooming in on that, I have to apologize. This is the data as it came off the ship, so I still have to literally iron out some of the noise. But it also highlights some of the issues that Steve Rock has talked about this morning with navigation of an autonomous vehicle. We leave our AutoSub to carry on its own work while we deploy the ROV in a different location. So there is a certain amount of drift on the navigation and a certain amount of unknown in terms of specific positioning. Still, it's even from this very rudimentary first processing, you can see some of the details where you see outcrops in the Talweg channel coming out, and then also this spur coming through with these small positive features. Zooming in on that, we then deploy the ROV bathymetry, pixel size around 10 centimeters. You can see those small lumps in even more detail, and our video survey confirmed that those are small cold water coral reefs. And using the HD camera, we can actually go down to individual polyps and understand the entire community. So that does become our tagline, from pixel to polyp, imaging all the processes at the scale they occur and understand the connections between those scales and processes. Our second challenge then was to extend that survey capability to also map vertical or overhanging parts of the canyon. And for that, we developed a solution already in 2009, where we were trying to get a good picture of a vertical or a very steep piece of the Whittard Canyon, as you can see from the cross profile there. And we adopted this method where we placed the multibeam echo sounder, which normally is downward facing to on the front of the ROV, and then we let the ROV travel laterally along the cliff to actually create this morphological map. It's a little bit clunky maybe, but it actually provided us with a very good point cloud, giving insight in the morphology of that canyon wall. As with any acoustic system used for mapping, there is always a trade-off between the area covered and the resolution you can get. The further you stay away, the more area you can cover, but the bigger the pixels will be. Also, for safety reasons, we started off quite far away from the cliff. And that gave us the opportunity to really map out the entire 120-meter high cliff. And as you can see from the color scheme there, the colors are according to distance from the ROV. That part of the canyon wall was really overhanging, which means that with normal downward-looking technology, you could never image that correctly. Coming in closer, we then finally could make the bottom map, which allowed us to map out every single bedding plane of the geology and every single coral colony on it. And if you think about this cliff being 120 meters high, and from our general bathymetry we understood that it's 1.5 kilometers long, you do realize that this is a very rich and a very important location within the canyon, hosting such a large cold water coral reef. You could also question, at 7 meters distance, what's the point of doing acoustic mapping? Can't you just switch on the video camera? In this case, actually, no. Because this location in Whittard Canyon is prone to very strong tidal currents, and the turbidity at some moments throughout the tidal cycle is such that I wouldn't be able to see the screen or the lectern at this distance. So using the acoustics, we actually can get an overview of that coral wall. However, as I said, flying the ROV sideways is time-consuming. The ROV goes at 0.5 or not. It gives really high resolution, but it doesn't cover very much ground. So last year, we extended that capability to our autonomous underwater vehicle, AutoSub 6000, by tilting the multibeam receiver head, reballasting the vehicle, and developing a control algorithm to track the cliff and having a collision avoidance solution, using actually the data coming in from the range finding from the multibeam. Putting all of that together, we then could carry out nested mapping in 3D. I'm now focusing on another branch of the canyon. And we're representing this as a point cloud. So the widely spaced dots in the background represent the bathymetry obtained from the ship, 1 pixel every 25 meters. Nested in there, we have the survey results of our AUV mission collected in a couple of hours survey time. And then zooming in even more, we did go back with the ROV sideways mapping because it still provides more detail, although to collect this piece of high-resolution bathymetry, it took us twice as much time as the AUV used for the entire section of the canyon. And of course, this kind of data then makes it much easier to correlate to the biological community, which in this location mainly consists of this combination of scleractinian cold water corals and large clams. And you can see actually how the clams and also the corals really stick to the more resistant strata in the geological outcrop. Our third challenge to include the water column information into this. That was mainly tackled by the glider, and as you can see from very preliminary results, our glider really resolved with its 10 profiles per day the internal tide within the eastern branch of the Whittard Canyon. In some cases, there were vertical displacements of up to 80 meters of the water mass. Now then the question is, how do we all put that together in a comprehensive way to convey that information? As I said, with the bathymetry, we use point cloud visualization. But also with the high definition video, we now try to develop ultra high resolution morphology from imagery and video. So zooming in onto one of those small cold water coral reefs, we used structure from motion algorithms, which basically use the information that they can get out of consecutive pictures of the same object, consecutive overlapping pictures of the same object, and create a 3D model, for example, of one of those small cold water coral reefs. And this is our very first result. a model like this gives us the opportunity to get a full overview of this cold water coral reef, something that is not possible in the deep sea due to the light attenuation. So in the deep sea, you can never see the entire reef at once, which you can do in this case. This also allows us to calculate terrain characteristics that we can derive from this 3D model, such as the aspect or the rugosity. As you can see here, at different scales also we can calculate that rugosity or the slope. And at the same time, it's also a source of information for detailed biological studies, where people are actually looking at the real spatial distribution of individual species in a 3D framework, be it that those species are like symbionts or always happening in the same community or just happening to be there at the same time. It allows us to really understand the patterns and who is living where with each other. And this then brings me to the 5th challenge, the last one. How to bring this all together. And that starts off with the coordination of the vehicles in the canyon during the operations. And people will ask me, so how did you coordinate those 3 different vehicles? And the long and the short answer, and I apologize if it disappoints, but in this case, manually. It was the task of the principal scientist, i.e. me, to coordinate the different dive plans of the different vehicles. And for example, we had the glider occupying specific stations for about 30 hours at a time, and then moving on to the next station, so getting a really good tidal signal for each location. Many of those stations were also our prime targets for the ROV and AUV surveys, for obvious reasons, because there were specific benthic communities. And so it was up to me to decide which vehicle was going in the water where, which leaves a lot of responsibility in the hands of the PI. Autonomous vehicles can go wrong, as Google has realized recently with its car crash. And that's part of technology development, but it meant that I had to set quite wide buffer zones around each of the vehicles operating, especially also thinking if there is a fault happening and the vehicle doesn't have any propulsion anymore, starts drifting with a very strong current in the canyon, I was playing it quite safe. It meant also that there was a certain limitation to the operations that I could plan, and there was a lot of transit also between working sites. So in the near future, we are now looking towards getting a better control on that. And the first step we're doing in that direction is to develop a common command and control front end. We're currently working with companies such as Seabite. We actually already have a web interface for the gliders. You see a picture there where we can follow the different gliders in the water and how they behave and how they interact. But we want to extend that to the other vehicles and indeed really include also the interaction. Secondly, we're also running an Innovate UK project to link surface vehicles with deep vehicles. So you see a picture of the unmanned surface vehicle, the Sea Enduro. And that would then act as a chaperone of our deep AUVs, constantly talking, giving updates in terms of positioning, probably also giving updates in terms of mission, or even giving the opportunity to send some data back to shore. And as a third one, there is also a small business research initiative towards developing an adaptive autonomous ocean sampling network where a heterogeneous and scalable fleet of long-range autonomous vehicles should be able to go in the water and work together to solve a task. Next step is then to bring all the data together. As I said, we use 3D point clouds for the acoustics. The glider information went into a hydrodynamic model, kindly provided by our colleagues of the University of East Anglia. All the environmental information we put together in a geographic information system. And then we combine that with our observations of specific species occurrences into species and habitat prediction models. For example, you see a random forest model here. Which then allow us to derive an understanding of where we can expect the highest biodiversity, specific species occurrence, and that allows us to provide advice to government. So on my wish list for the future, I think better integration is one of the prime tasks in the near future. Better integration in terms of operations. As I said, it would be ideal to have more vehicles in the water at the same time, closer together. Also having the opportunity to work in several of the canyon branches at the same time to see how the internal tide, for example, affects the different canyon branches and the sediment flows and the communities at the same time. Automated coordination, as I mentioned, and these squads of vehicles that can work together. Also better integration in terms of the multiple scales, smoother transition between the scales rather than going plonk, plonk. Really a better integration, and the presentation about medical imaging actually hinted at a similar problem, how to put images from different sensors together. So there might be an area of overlap there. In terms of water column and seabed, developing one coherent, fully three-dimensional GIS. The other one, which I haven't put on there, on the long run, to better understand where the biological communities occur. The one factor that we haven't got in our models yet is the biogeochemistry. Those communities need to live off something, they need to eat something. So information about the food input and the food quality coming down to the corals, for example, would be very helpful in our predictive habitat modeling. And then driving towards the smooth integration of all these different models for species prediction. So altogether, the CodeMap cruise and the work we've been doing gives us the first 3D picture of a submarine canyon. We can now actually collect information that we could never obtain before, for example, morphology under the overhangs. We get a better understanding of this complicated environment, and those vehicles and the fleet of vehicles allows us to acquire sufficient information within a reasonable time frame. We're not sitting there for 200 years doing CTDs, to actually build up a good image, and on the long run, this should then drive towards efficient future monitoring for environmental legislation. Hopefully working with a fleet of vehicles that has a coordinated operation mode. So this brings me to the end of the presentation. I would like to thank the funding sources, especially also the teams that came out to see to make this all happen. And if you would like to see any more, especially also very nice deep sea video of all the communities, have a look at the cruise website.
We have time for 1 or 2 questions before we move on. Anyone? Yes?
Were you pleasantly surprised on the environmental modeling and environmental monitoring, or was it nasty surprises?
Actually, we were pleasantly surprised. We did find some really nice communities. In some way, the very steep terrain of Submarine Canyon kind of protects some of the communities from too heavy impacts. No single trawler will try to trawl a vertical wall. It would also not be possible. Unfortunately, on the negative side, we did come across, as I mentioned, a lot of lost fishing gear. So there is a lot of ghost fishing going on, to the point that it's actually increasing the risk of our own vehicles in the Submarine Canyon. That was another reason why I didn't sleep that well most of the nights, thinking of every other ROV dive we would come across a lost line, a lost net, so yes.
Yes, question there?
My name is Charles from ASTER in China. Given your experience and expertise in this matter, has the identified MH370 been a surprise to you, or do you think there's something else that's being talked about?
Of course, that's not a biological community, but it is more than a needle in a haystack. So, as I mentioned, we are dealing with vast terrains it's an enormous step forward to be able to have 3 vehicles in the submarine canyon at the same time. But if you look at 200 kilometers and the amount of area we could cover in 5 weeks, no, it's not a surprise to me.
Yes, one last question.
Any plans for involving in-situ chemical detection for the underwater vehicles or other parameters that you can integrate into the vehicles to get more information since you are already in the canyon?
As I said, on the long run, I would like to start looking at the biogeochemistry parameters. I haven't got much experience or expertise in that background, so this is the first time we're really putting hydrodynamic models into habitat suitability models, so that's characterizing the physical environment. Putting that biogeochemistry in it would drive it even further.
There was one question here. Someone had their hand up, or should we move on? We started 5 minutes late, so we're not behind schedule, Ralph, I assure you. Okay, if there are no further questions, then, okay, one more.
I was just wondering, when in the future, do you see any applications for a larger group of vehicles operating in close proximity, the real-time communication between them, where you really need them to be in contact, that they can do live adaptations based on what they see?
I think that would be a fantastic thing to be able to do, because as I said, the submarine canyon is a very heterogeneous and variable environment, and that must also be the case in the water column. So be able to follow specific features as they go through the internal tides, and for example also small sediment flows coming down and stuff like that, that would be fantastic, yes.
Great. Thank you, Veerle. Okay, so now for something totally different. In the opposite side, we're going to go to the atmosphere and terrestrial interface with Dr. Andres Diaz from the University of Costa Rica. Andres received his PhD from the University of Minnesota. Andres.
Well, thank you very much. I would like to start with thanking the organizers and also Chris for inviting me to this venue. It's quite an honor. I think it's the first time that somebody from my country, from Costa Rica, is here in this venue. And being a physicist and knowing who has spoken in here, it's overwhelming. So I just wanted to thank for that opportunity. And also, it's also motivating because my father is an oceanographer. So I'm a physicist, he's an oceanographer. He was the first one who put a remote control vehicle on a crateric lake in my country to investigate the salinity and the temperature on an active volcano. So I think I come from that background, and for me to be in this Catch the Next Wave conference is also very an honor for the family. I just wanted to talk about what I'm doing in my research work, which is implementing unmanned airborne mass spectrometer systems for dynamic in-situ volcanic plume measurement. So we are trying to monitor volcanic plumes, basically. And also I want to also acknowledge my colleague, Dr. Robert Klein, who is here from CRARE. For the small universities to collaborate in this, to work on these areas, we don't get a lot of funding. So when funding lacks, creativity flourishes. So we need to really come up with good collaborations and good ways to answer the same questions that everybody's answering. Answering the same question that everybody wants to know is, well, when a volcano is going to explode. My house is sitting 20 miles as the crow flies from a volcano, from this volcano, which is Turrialba volcano. And I want to know, I want to use kind of the knowledge that I have or the technology that is available to understand better the system that could cause damage to my city, my family, my country. So basically that's the motivation for me doing this type of work. And I will tell you a little bit how that started. And also I want to acknowledge all the collaborators. Again, without them, we will not be able to do this kind of experiments. NASA, for instance, is one of the big users of the information that we collect. I fly, every Friday we launch a balloon from my lab, and then we collect different data, especially ozone data, for validating some of the NASA satellites. And in those balloons, we have payloads that are $4,000. They are for measuring very precisely the water in the upper, in the stratosphere. And we lose, that's a $5,000 payload. So for volcanic sampling, it needs to be almost the same concept. You need to have a payload and a vehicle that you need to afford to lose. Why? Because an erupting volcano is very harsh environment. It's very disruptive. You cannot expect to survive after you go through one of the plumes, basically. So we need to develop technology that is not only unique, but it is affordable. So that's some of the requirements. Other people that are users of the technology is JPL, also USGS, INGV, which is the Italian volcanology agency. So I'm collaborating with a lot of the volcanology institutions who needs technology being developed. So what is the problem that we are trying to resolve? Why volcanic plume characterization? First, volcanic airborne emissions can be devastating to have economic effects and a direct threat into the human life. We all know that. We all, especially in our countries that are in the ring of fire, we know how disruptive a volcano can be. Now, also for people who don't live near volcanic areas, they know, especially here in England, with the Iceland volcano erupted, the airplanes were ground for weeks, and there was not enough information to really make that decision. There was a threat, there was a risk. But when a risk happens, you need information, and that information needs to come from in-situ data. Satellite, current remote sensing, retrieve and transport models lack enough in-situ validation. So you have an image from the volcano, but you don't know exactly what is the right amount of concentration of ash, for instance, that is in the atmosphere. For that, you need to validate what the satellites are telling you, how you transfer that picture that you are seeing in 2D to a 3D model that then you can tell, well, it's going to fly over England, so stop all the air traffic over Heathrow. So that's basically the problem. This has been a chronic and persistent problem identified in domestic international forums. For instance, the other picture here is from Turrialba volcano, which I started to investigate when I finished my PhD, I don't know, like 20 years ago. And last year it finally erupted. So it was a dynamic system. So it started from some small fumaroles to an erupting volcano. So it has been kind of a very interesting natural lab where to test new technology and your ideas. So for volcanic airborne emissions, gas and ash, they provide fresh and up-to-date information on what's going on in the interior of the volcano. They provide, for instance, what kind of magma. I mean, do you need to really worry about the activity, or you think it's going to settle down? Now, there's also difficulties in predicting the trajectories and the extent of the drifting ash cloud. So that has led into the encountering of several planes with volcanic ash, and in some cases, almost making the aircraft to crash. So there's a need for a better understanding of the properties and internal chemical and physical process within volcanic plumes. So that's really what we need. We need real data. For instance, the information that the satellite collects this is the image that is retrieved. And from that, it needs to be transferred to a model where say, well, there's probably ash in this area, so please don't fly in this area. But that decision implies millions of dollars. So why don't take that part of that cost and put it in the front end to understand exactly and to validate what the satellite is telling. So that's basically what we are trying to do with our small project, is to validate something that is very visible from space, which is in a volcanic eruption. So the solution in our case is to use UAVs. It's an in-situ volcanic plume analysis from small unmanned aerial vehicles, so that we can monitor the volcanoes and use that data for the calibration validation of satellite, and also to do aircraft-oriented air quality assessments. We want to do that with measuring ash, some of the volcanic precursors or chemicals that you will find in a volcanic eruption, which is SO2, H2S, CO2, probably other gases, but we don't try to monitor in exactly where the eruption is, but on the plume when it has diffused a little bit. So the concentrations will be higher for these three gases mainly. We want to measure as any radius on temperature, pressure, and humidity to validate the physical models. We want to correlate every data with a GPH location and altitude. We want to collect fresh samples as well. And then to that, we need to develop either to get commercial off-the-shelf instruments or adapt them to the UAV. And for that, we have used electrochemical MEMS-based SO2, CO2, and H2S sensors. And how this started was to the development of a miniature mass spectrometer. That was my topic when I did my PhD in the University of Minnesota. My professor told me about my background. I said, well, I collected samples, and one of the areas was volcanic samples. I went to the field and collected the sample and brought it to the lab and then analyzed it there in that case was a nuclear activation analysis. I said, well, why don't you use a mass spec to go to the field? Well, mass spec is this big, has a lot of power, needs a vacuum system, so you really cannot bring it to the field. Well, that will be your PhD topic, so that you will need to work on that and develop it. So I spent 5 years understanding first the field, because I was not a volcanologist, then understanding MEMS at this point, microelectromechanical systems. So that's my minor is in that area. And finally going to the field and applying it. So what is the strategy? Well, we want to pretty much have simultaneous UAVs sampling the volcano and erupting volcano. Some of them could be in tether aerostats that are stable there, collecting data over long periods of time. Some of them will be in a distal zone with minimal risk, but they have more expensive equipment. But some of them will be flying through the plume, and in that case, we'll need to have very inexpensive payloads and very inexpensive UAVs. So that's basically what we are trying to achieve, and that's a project that NASA started like 5 years ago. We were at a conference, and I was doing my work in miniature mass specs, and they say, well, you know, we need to put a mass spec on a UAV. Well, let's try to work on that. And then that has become the topic of this research. Then we started collaborating with companies like Creare, who allows us to integrate, and then also they have a vacuum technology that allows to the miniaturization of the vacuum system. So that now you have a miniature mass spec with a miniature vacuum system that you can put on a UAV. So the benefit for that is, well, first, basic science of eruption prediction. We have more information that otherwise is not possible to collect. Because you don't want to put a volcanologist near an erupting volcano, even though I have a lot of colleagues that are volcanologists, and they like to be there when they're on an erupting volcano. And they are thrilled about the, I don't want to be there, basically. I want to be as far as possible, so that's why I'm using a UAV. And then also that calibration validation of the remote sensing data improves the models, improves the quality of the models to make decisions that impact people, and it has a lot of effect also economically. Again, how much money did Europe lost by having all their planes ground for weeks? I don't know, I would like to get an estimate on that. I haven't had the time to do it, but. So there were previous milestones that we were able to do during all these years. One, first to develop the miniature mass spec system and then going to the field. So in the first characterizations that we got, this was 2 days after an eruption, so we monitored the fumaroles. This is with a mass spec on a backpack in this area. And we were able, before the eruption, we didn't see any helium, but then after the eruption, we got a very clear signal at 4. So we made it to the International Journal of Mass Spectrometry, because it was kind of the first evidence that you do have a fresh flush of helium before an eruption, and that can be used for predicting activity. But again, you need to have a system on the ground to do that. And you don't want to be there when the volcano erupts. So at the end, okay, we need to move to another platform. And then the UAVs, which has spike in the kind of, the cost has going down and the technology has going up. You have more control of the platforms. And then they can, each time they can carry more weight. So it has been a good time to be in this area to develop this project. And again, with low funding, we cannot imagine having the funding that some people have, for instance, for underwater autonomous vehicles. We cannot really, we will dream about having that kind of funding. But we don't, but then again, we use what we have and we use the resources in the most effective way that we can. And at that point was to use balloons. So we went before below the plume, and then we launched the balloon with some sensors, and when we started plotting the concentration and why the satellite, in this case the ASTER satellite, was collecting data. So we were able to collect in-situ concentration of the volcanic plume while the satellite was taking imagery above that. Then, well, that's a picture of my the mass spectrometer that I developed for my PhD. It was a double focusing magnetic sector mass spectrometer, and then kind of that was the culprit one that initiated this, applying the mass spec to the field, going to the field, making measurements. But then they become very dangerous to be there, so we started using the UAVs. And this is the vector wing UAV. This is the one that we are using in my university to collect some of the information and the data. Then we develop instrumentation. It's called a MiniGAS. And then this is an in-situ payload that has different sensors. It has a SO2, H2S, CO2. It can send the data by telemetry, so we have real-time data. And the reason we have real-time data, and also we have onboard storage of the data, but the reason we have online telemetry is that we have lost payloads. We have lost the vehicle, we have lost balloons. So in some cases, the data that you are retrieving is as important as the payload itself, or even more important. So we don't want to go in, and when we are in the tropical forest, so sometimes we cannot really know where it landed. We have the beacon, we have other technologies to try to go and find them. We know what it is, but we cannot get to that. So this is the payload that we have kind of putting together. First, it was the alpha version, then the beta version, now it's the NTX version. And then the next version will be one who has a mass spec, and then I will talk about that at the end of the presentation. So this is kind of the information that we want to get. We want to launch a balloon or a UAV and get a vertical profile of the concentration. So we know where the plume is, we know the altitude. So here in the x-axis is the concentration, and then the y-axis is the altitude. And then by knowing what is the thickness of the plume, that sole information is important for the people who are trying to model, because they just get a 3D image of what's going on. So we can at least give them what is the concentration, what is the thickness of the plume, and then they can get that into their modeling. And then we correlate that with ASTER concentration. So for instance, in this case, we were able to get a very good correlation between ppm, parts per million. It went up to 6 ppm, and then our in-situ concentration also went up to 6 ppm. So in that way, we are correlating and validating and not calibrating. With the calibration, we are still not in that stage, but at least we are validating some of the models of the satellite data. Okay, so then we move to use a UAV, and then for this I want to present a small video on kind of all the development that has, so it's easier to imagine kind of development that went into going from using just balloons to the UAV and the type of deployments that we are doing in Turrialba Volcano. So my lab is the GASLAB, and this is the eruption that we had last year in March. So that's our target. Our target is trying to fly a UAV through that plume. And then again, all of our collaborators and institutions that make this project possible. So we are here in England, and then for those who don't know where Costa Rica is, that's how I put this map. So we are in Central America, so in the middle of the country this is the Central Valley, is called, that's my lab, and the University of Costa Rica is situated there. In Turrialba is like 30 kilometers away. Then we first started with balloon launches, tether balloons, in-situ sampling. So again, just a couple sensors put together and wrapped together in duct tape. And then we started launching through the Plume and collecting vertical profiles. And we did that every 16 days. So, and then we were retrieving the data at the same time and producing these maps that we then correlate with the satellite data. Then we get plumes like data like that. Then we move a little bit into from the alpha to the beta version, still on tether balloons, to develop the technology a little bit more robust. And this is 1 year before we have the large eruption. Now we cannot launch from that side because it will be dangerous. Then we move from the tether balloon platform to the UAV platform. And then we call it the Vector Wing 100. And the first 100 meters is manually controlled, then it goes to an autonomous stage. So where we pre-plan the flight, or we can, with the computer, tell it where to go. It has a camera, it has of course, all the media was like crazy when we were doing that, because it's quite unique, and then I think that's the reason I'm invited to this conference, because we are trying to do something that is difficult to achieve, and again, it's not widely popular to do this kind of measurements in the volcanology area. So we're flying actually through an eruption. So we accomplished that last year, and then of course the plane was too far away, but we get it all covered from ash, and then we collected that ash, and that was sent to JPL to analyze. So we at least got one of the objectives was collect fresh ash from an eruption. This is kind of the flight plan, and also the data that we got. So red means higher concentration, green means lower concentration, and that data has already been published. I'm also working with the University of Alaska in Fairbanks, and then to develop that capability, but with drones, so that they can use it in their volcanoes. USGS has a payload, and Alaska has another payload. So they bought one of my payloads to integrate that into their tools for assessment of volcanic assessment and measurements. And then at that time also Italy got involved, and then we went to Solfatara, that's in Naples, and then we flew the same payload. Now this is our octocopters that are capable of carry up to 10 kilograms of payload. And then from Naples we went to Volcano Island, and then we did the same measurement. First, a ground survey, so I carry the instrument on the hand, and then I get the concentrations at the site, at the fumaroles, and then we put the same instrument into an octocopter, and we are able to fly it. And then the next step that we are doing is now not only the MiniGAS, we are actually testing mass spectrometers on the field, because that's what we are trying to achieve, is to put a mass spec on a UAV and do the same task that we did last year with the MiniGAS. Okay. So this is the information that we got, the 3D mapping that we are able to acquire. So about the mass spec that we are developing, this is, we have two platforms. One is using large UAVs like the Sierra from NASA, and then the other one is a smaller for like the octocopter or the Vector Wing 500 that we are developing. We use technology, one is from Inficon. The story why Inficon, my mass spec was licensed to a company, then that was sub-licensed to Inficon that uses now as a commercial product. So I have a good relationship with them, and then we were able to get some of their mass spec and to buy some of their mass spec for this characterization. And then at the same time, CRARE has been, we got an SBIR for the Resolve mission, so we started putting this package together to having a mass spectrometer for a lunar lander. But in this case, we try to use, we are also trying to have a system that we can deploy into a UAV. So we are using some of the CRARE small vacuum pumps to enable this technology. So for the mass spec, this is a miniature mass spec as well. This is a quadrupole mass spectrometer that is just 2 centimeters in distance, the 1.8 centimeters quadrupole. The pumps, they are miniature pumps. They use very low power. This is a drag pump, and also they have a turbomolecular version that we are using, and also a miniature backing pump, again, low power, low weight that we can put together. And then we tested last year in different sites in the ground in preparation for this year where we are testing into the UAVs. So this is in Volcano, again, trying to monitor what gases are there. For instance, the degassing happens in the water, in the soil, so we are gathering the main gases. And then this is a couple of weeks ago when we are getting ready to flying the mass spec on the Sierra airplane. That one has a 100-kilogram payload, so weight is not a problem. But that UAV costs $500,000. So if I lost it, then NASA will never speak to me again. So for that, we are just using it in California in a very controlled site. But for going to the real deal, we are finishing this version, which is the Vector Wing 500, with a 4-kilogram payload that involves the mass spec and the MiniGAS. So our work has been kind of, again, people are looking after our work because it's new, so we made it to the last year, the cover page of the Journal of the Mass Spectrometry Society, because, again, it's the first time mass spectrometers, I know that there's other groups doing this as well, but we have been able to go a long way in a few years to put a mass spec on a UAV for volcanic measurements. And this is how it looks for the future. We are integrating the mass spec, the MiniGAS, into a version that has the octocopter and also the one that I just showed you, the Vector Wing 500. And so with this, I go to the last page. We have established a systematic plume characterization method at our volcano at Turrialba. We have developed a low-cost UAV platform for in-situ volcanic emissions. If people have technology that they want to test in volcanoes, let me know. We're happy to put it on the UAV. Or it's a nice natural lab where to work because you can go to the volcano with your car, and then we understand, we kind of understand now what's going on with the volcano. So it's not that dangerous. Okay, so I'm going to end here, and because time is up. So thank you very much.
Any questions for Andres? Yes?
My understanding of the Iceland problem was not gas, but it was fine particles, glass and carbon.
Yes.
And you said so.
Yes, that's exactly we use, I mean, the society, or the Volcanology Society, uses SO2 as a precursor to understand where the ash cloud goes. But there's a big difference. And I have seen it in Turrialba that the SO2 plume goes one way and the ash plume goes another way. So one of the part of the research is to understand that difference and saying, hey, you really cannot predict where the ash is going to go by measuring the SO2. I mean, you need to understand the physics of it to help your model. So, but the only way to do that is by using data, real data, the model gives you an idea, but you need to validate how your model is behaving. And that's what we are trying to provide by collecting ash data and gas data and doing these profiles to understand the difference, how it's really behaving.
Another question? Yes, up there.
Is it of interest and indeed feasible to map the plumes as opposed to just sample them the way you
So we started, yes, I think the videos just show some of the traces where we are trying to do an active map. So basically, you will need to set up a 3D grid to do that. Now, the problem is that the plume gets in your way. So it really depends on how hard your plume is. And in some cases, the data is so needed that just a one time going through the plume and it's like sampling tornadoes, okay? Sometimes the information is, we know very little about it, and just getting one probe to survive a volcano and give you information of the inside of the volcano helps to understand what is the physical process that is going inside. So that's the same thing with volcanoes. Now, we would like to have a 3D grid when the plume goes in, and then we can do all the characterization, but we are so data poor that anything will help.
Any other questions?
Yeah.
Yes, wherever you are.
How often is helium 4 used in terms of volcanic prediction?
Well,
4 days is good.
Yes, well, the volcanologists, for instance, they take a sample, they bring it to the lab, and then they want to characterize or differentiate helium-3 from helium-4, and then they see the difficult difference in the isotope composition. And then they will be able to tell if it's magmatic or not. But there hasn't been enough mass specs in volcanic soil sampling 24 hours to understand the flow of helium coming from a shallow magma. So to answer that question, what I need to put is a mass spec 24 hours sampling during an eruptive period to understand how the concentration varies with time, and that will give me, because they are doing already that with SO2 and H2S, but SO2 and H2S are very affected by the weather, by water, by other compositions. So helium is a very nice gas because it doesn't correlate or doesn't interact with almost anything. So that's exactly what I'm doing. Another part that has not to do with UAVs, but is to put helium detectors in the ground, and I'm putting one in Turrialba and another one in Italy to sample for a long time and understand exactly that question. How soon or how much before an eruption can the flow changes, and so I can detect that change. And each volcano has its own kind of personality. So you need to understand not only how different is, how this particular volcano behaves, but how different it is from another volcano. Again, and you can, I don't know if that explains, if I answer your question. Yeah.
There was one last question, then we'll have to move on. Yes.
And also from South Africa. Have you tried that with forest fires? Because if we would measure also volatile organic compounds and then have a CPC for particulate measurements, so that would be ideal for studying wildfires everywhere.
Yes, I have not tried with wildfires. I know that the NASA Sierra UAV, they sometimes is called for monitoring, and they're using other instruments, and they have. They told me that people are interested in using the mass spec for that application, but I have not started to work on that application. Yeah. Thank you.
Okay, well, let's thank Andreas for his presentation. 2-centimeter quadrupole mass spec that runs in less than 10 watts. That is impressive and would be phenomenal if we could put that in the ocean. Our last speaker for today's session is Dr. Ed DeLong. He comes to us from the University of Hawaii, and he received his PhD from Scripps Institution of Oceanography. Without further ado, Ed.
Thanks, Chris. So it's a great honor to be here today, and awesome in a way thinking about the sorts of lectures and events that have occurred here at the Royal Institution, and that includes the talks that we've heard today, which were all really amazing, and I know I've learned a lot. I have to, full disclosure here starting out, I am an end user. The closest I'm coming to autonomous vehicles is I've got wireless on, and I'm going to be remote and autonomous as I give my talk today. I also really enjoyed the first talk today, thinking about technology curves and the different places that we all join in on them. I would characterize myself as a too early adopter or a technology parasite, maybe a combination of both of those. So what I'm going to do is just break down. I also, final disclosure, I'm a microbial chauvinist, and so I'm really going to be focused on thinking about the microbial world writ large around us, really basic knowledge, trying to understand what's going on in this tiny world that impacts our own planet greatly, but that we haven't really been able to observe that well in the past. Lots of times over the course of the history of microbiology, it's in fact over the whole history of microbiology, technology advances have really advanced this science greatly. So let me start out with the why of microbial oceanography, my own particular area of expertise. You may think about different things as you look at these beautiful satellite photos of chlorophyll from space. Myself as a microbiologist makes me think about how widespread and pervasive the microbial world is. The forests of the sea are microbial. You can look at this and see how there are different blooms and busts that are physically and chemically forced by changes in the ocean. One other thing to realize as we watch this is that these are super tiny organisms, microscopic, that we see from space. They impact biogeochemical cycles greatly. I like to think of them as massively parallel, broadly distributed processes of matter and energy, and in fact, these tiny microorganisms are the responsible agents for making many biogeochemical cycles turn on Earth. And that in itself makes them a very interesting topic of study in the context of, for instance, changing biogeochemical cycles on our planet. As I mentioned, the forests of the seas are microbial. In fact, one of the most abundant plants on our planet is actually a cyanobacterium known as Prochlorococcus that was only discovered about 25 years ago using flow cytometry on ocean samples. So we're still learning a lot about the sorts of life that's out there living in the ocean. And the other thing to remember is that these organisms are extraordinarily abundant. There's more microbial cells in the ocean than stars than we can see in the sky. And they are not static. If you look in surface waters, for instance, turnover time of these cells is on the order of a couple days. And what that translates into in terms of cells produced per year and consumed, the turnover time, it's numbers that are astronomical. We can barely think about them. And these are all biological events. The predator-prey relationships, viral lysis, mutational events, gene exchange are all occurring as these cells are turning over on a daily basis in the world's ocean. It's an important part of the ocean that we're still learning about and need to understand. And I already mentioned that from ocean surface waters down to the ocean depths and even down to the deep subsurface, these microbes can be found. The current temperature limit of life is about 114 degrees Celsius, and you can find microbes in almost any habitat on Earth. Okay, brief introduction on some motivators, but let's get down to brass tacks here. One of the main things I'm going to talk about is actually convergence of two different evolving technologies that have really advanced very rapidly. One we've been hearing about today throughout the course of the morning and this afternoon is robotics. The other area that I've been more heavily involved in actually is the development of genomic technologies and actually its use in environmental survey, monitoring, characterization of microorganisms. So what we're really trying to do is bring together these two evolving technologies and have them work together to help us understand the world around us. Now, another disclaimer, the microbial world is extremely complex. This is a little whimsical in terms of all the activity happening in a single droplet of seawater, but suffice it to say there's a lot going on with respect to the diversity and the interactions at many, many, many different scales. And so the scales I'm going to be talking about today, in terms of some of the sampling and analysis we've been doing, is on the order of about a liter of seawater, that is. And really, I'm going to focus on sampling in time as opposed to space, although space is of great interest too. On kilometer scales, looking at mesoscale features like anticyclonic eddies and those sorts of things, which out in the ocean I work in, north of Hawaii, are really important physical features that characterize that habitat. So what are we doing sequencing DNA from microbial communities to try and understand what's going on. And this is just a graphic pictorial way to think about it. Imagine these are genomes of many different species that are co-occurring in a particular community or assemblage. Well, now it's possible to actually sequence that assembly en toto, look at the DNA sequences and make inferences about the kinds of microorganisms and viruses or phage that are there, how they may be interacting from some of the clues that are present in that DNA information. And also, the genes from that DNA encode the proteins that catalyze lots of the biogeochemical cycles that we're interested in, cycles of nitrogen, phosphorus, carbon, and so on. So also, where those genes are found in a particular habitat and when they're expressed, that is when they're active, tells us something about what's going on with community metabolism that translates into biogeochemical cycles. And from these sorts of informations, we're trying to make inferences about what's going on in the ecosystem. Another way to look at it is to simply think about the simple canonical central dogma of molecular biology. DNA basically encodes the parts list for a given organism in its genome. The RNA basically is a copy of each gene, and when that gene's turned on, that RNA is made, and then that RNA is translated into proteins, which are basically what gets the job done in terms of cells. So you can think of it as the machine language, the assembly language that codes and instructs these sorts of things that allow us to answer some very basic questions that 20 years ago we couldn't even really approach. Just a simple question of who's there, taxonomically or phylogenetically, what kinds of organisms are in this habitat, and how do they change on seasonal scales or daily scales, that sort of thing. What are they doing, especially with respect to biogeochemical cycling? What sorts of different functionalities are there, and how do they change? And then looking at the dynamics of that in both time and space. These are the sorts of questions that we're interested in asking. Very generic, I admit, but I'll try and get to how we get more specific about this in a second. So this is just a reiteration of some of the things that we're going to try and measure, but measure in the context of oceanographic space, and particularly I'll be talking about the upper ocean. So the other thing we have to worry about, of course, is not just the diversity and processes within those assemblages of microbes, but of course the context of the environment around them. And of course these temporal and spatial scales are extraordinarily complex in terms of trying to map what's going on in particular contexts of time and space. The ocean's undersampled. I think that we've heard that in a number of talks today. And again, what I'll be talking about today is really thinking about sampling in the order around here over the course of hours to days to weeks. What happens in the daily life of a microbe or microbes in complex assemblages in the upper ocean? And what does that tell us about how microbes interact and what's going on with respect to their biology? So what we really would like to do, and this is kind of the core of what we've been doing in collaboration actually with Chris Scholl and colleagues at the Monterey Bay Aquarium Research Institute, is try to take a motion picture of microbes on pretty short time scales in the upper ocean. So how are we going to do that? It would be nice if we could dive in with an electron microscope and really look at the very small scales. We're not there yet. So what we're going to do is sample a liter of seawater and use genomics to help us take a picture. One way to visualize that is that this is our film. This is how we're going to start taking the motion picture. We're going to collect an assemblage of microorganisms. And from that assemblage, we can make either DNA or RNA to get at the parts list of what genes are there and what genomes are there, what kinds of microbes are there. And then the RNA is when are those genes turned on, and what are the dynamics of that within a species, but also between species. What does that tell us about the biology? So that's our film. And our camera really is the invention. Oh, by the way, the collection of this genomic DNA, just as a side note, in a robotics conference, this whole technology, which has just exploded in the past 10 years, was driven by robotics, robotics in the laboratory. But let's talk about robotics in the ocean. This is going to be our video camera then, because the ESP that Mbari and Scholl developed has the capability as an electromechanical fluidic device of taking a sample and then basically preserving that sample so that it can be analyzed downstream upon recovery on shore using these kind of techniques. So I'm not really talking about in-situ sensing, but I am talking about preserving those little snapshots of microbes over time so that we can start to take the motion picture. First kind of baby steps to understanding dynamics in the microbial world. When we first deployed with Chris and friends, the ESP in Monterey Bay to do this sort of thing after a lot of validation for preservation techniques and so on, we did it on a mooring. And really what we were after is, like, as I said, the day in the life of microorganisms. The problem, of course, with putting the ESP on a mooring was that what we were really sampling was not microbial populations in time, but rather the superhighway of microorganisms passing that fixed mooring in space. So we had to kind of deconvolute the space and time problem, and of course the way to do that, well known in oceanography for a long time, is by conducting Lagrangian sampling. And so what we did was to put the ESP on a drifter, that's the royal we, that's really Chris Scholin and colleagues, and then take those snapshots over time in drifting mode in Monterey Bay. So that was our very first experiment, and it proved to be remarkably successful, at least in terms of validating the approach. So this is just a picture of that first experiment. What we're doing is getting the contextual information using, typical standard CTD sensors, and the output shown here. But at the same time, we collected those snapshots, those samples. Each of these points here represents a snapshot over time as the ESP is drifting. And then from the RNA sequences, we can infer the sorts of microorganisms that are there. The most abundant RNA transcripts were from a very predominant photoautotroph in Monterey Bay, Austriococcus, a very small pico-eukaryote. And then kind of some of the usual characters we expect, Synechococcus. These are all heterotrophs. I don't expect you to know those organisms, but they're very widespread throughout the world's oceans, and yet we don't really know that much about their biology. So now we're going to get to look at their dynamics basically in real time. So we have kind of a validation for this too, because we know from laboratory experiments and have very strict expectations about how the cyanobacteria and the algae are going to behave. Because just like us, they have very strict circadian rhythms. And in fact, we can predict which genes should be behaving in kind of a 24-hour oscillating cycle in terms of gene expression. And that correlates also to cell division cycles and so on as well. And in fact, that's what we saw. So the two dominant photoautotrophs in those samples, now these are samples from the ESP. We took those snapshots, we extracted RNA, we inferred the genes that were there and being transcribed at different levels over the course of a couple 24-hour cycles. So using harmonic regression analysis, you can get curves like this over a 24-hour cycle. And in fact, the genes that we saw cycling over a 24-hour period correlated very well with what's been seen with pure cultures in the laboratory. So that means we were able to float around with the ESP and take basically snapshots using these molecular methods to see what these organisms were doing in complex assemblages. And we can then ask questions about what time of day or particular pathways turned on or turned off, and what might that tell us about the physiology of these organisms. I'm not going to spend a lot of time on the science, but what I will say is that now we can look across many different species, and one of the big surprises, even from these first couple studies, was that all the organisms are involved in a very, I would say, highly choreographed dance out there. That is, it's not just random behaviors of this microbe doing that and this microbe doing that. Rather, there are staggered transcriptional cycles of particular genes that seem to be passing from one organism to the other at the same time each day, day after day. It's a highly ordered system. It's not chaotic, and in fact, it's somewhat predictable. And what we believe, and this needs to be validated, is that these gene expression patterns we're seeing with particular organisms, not just in kind of fundamental pathways like respiration, but also less universally distributed ones like carbon monoxide metabolism, for instance, are going to tell us something about the interactions between the organisms and also the biogeochemistry. So that's what I'm going to say about the science. Since this is a robotic conference, I'm just going to say a few words about where we think this is headed next. And part of this is really a collaboration between the NSF Science and Technology Center that I co-direct with Dave Carl and the Monterey Bay Aquarium Research Institute. And so Chris and colleagues have been involved in developing these TEPIS-class long-range AUVs with a third-generation ESP, which you see depicted here. I'm not going to talk a lot about that. That's Chris's thing. But the hope is, you know, we were at the mercy, basically, of the ocean's circulation patterns as we did those Lagrangian drifts. But with a vehicle that can basically sense things in the environment, that also has its own kind of vehicular capabilities, you could do a lot more in terms of mapping microbes in terms of space and time, as well as an event response. And so that's the kind of goal of this project, is to use a number of vehicles like this. And what Chris and his team have already shown is that these vehicles can actually autonomously sense features. In this case, this is the chlorophyll max. And then once they know they've hit the chlorophyll max, they can autonomously sample. And this was one of the first validations of that by Chris and colleagues. The other thing that we heard about, and I think it's a really good point to make, is that being able to coordinate a number of vehicles in the water is going to be a very useful capability. In this case, what you see, and this is again MBARI's operations, is a wave glider that's kind of serving as a tender or chaperone for two long-range AUVs, one called Daphne, which is basically doing circles around Mackay, the sampler, to get the oceanographic context, and then the Mackay is basically able to take samples in that context. So where we're headed with this, and it's kind of science fiction now, but it's on the horizon, we think, is being able to conduct operations like this and be able to, in essence, map microbial DNA, genes, taxa, biogeochemical capabilities in time and in space, along with the physical and chemical oceanographic features that these vehicles can collect. So imagine we were able to do that. What challenges does it pose? And there's many challenges, obviously, from operations to data collection to data interpretation and visualization. All these things are actually super challenging, but I'm just going to focus on one that has to do with the development of the technologies. So we have in Hawaii been conducting operations somewhat like this, with lots of vehicles in the water. These are kind of 3D representations of mapping around some of these mesoscale eddy features. Again, remember, our goal is to be able to sample and do the high throughput massively parallel DNA sequencing to map microbial features, taxa, genes, metabolic capabilities onto these same maps. So we're not there yet, but there are going to be some challenges, but we can get there, and we can get there pretty rapidly. So I just want to show you a little bit of data in terms of the numbers that we expect, what we think we see on the horizon, and then a couple challenges. So what happened here is basically new technologies were developed. Wasn't that long ago, only about 10 years ago. We've been teaching a summer course at Seymour for about 10 years. That's our center. And so we started teaching the summer course here, and we do a lot of sequencing in this course. And then over the course of the past 10 years, it's been a frantic, basically rewriting of lectures every year, trying to keep up with the technology and also give the students laboratory experiences in that course. So this is one way to look at it, is just the cost per base pair. It's gone down dramatically in a much steeper curve than would be predicted by, for instance, Moore's law. Another way to look at it is just the amount of data that can be produced per day, and this is kind of phenomenal. So up here, we're not too far away from about 10 petabytes of data for one machine per day. We're almost there. This isn't actually a bad estimate. In a final estimate that's more recent, if you take a look at the number of human genome equivalents, the human genome's about 3 gigabase pairs, where we are now is almost at about 1 million human genome equivalents produced by these DNA sequencers. And projecting out, if we went at the same rate that it's been going, we'll be at 1 billion in a little after 2020, which to me is staggering. It's mind-blowing. This technology has advanced faster than anyone I think might have predicted. And also it's been a huge game changer across all areas of biology, from environmental science to human health in essence. So it's really impacting folks that like to study biology greatly. But that's not all, because there are disruptive technologies as well that are coming online, and so that curve may even be totally blown out of the water for all we know. And for the purposes of this talk, again, this is a little bit science fiction, but what we think is that these technologies can probably pretty soon, they're low power, low data throughput, be applied on different sorts of vehicles like these for real-time data generation while you're in the water. There's not a super hard driver for that, for looking at whole communities, but the fact of the matter is it probably will be possible, I'd say in a 5-year window, to do these sorts of things. So what does the data look like? Well, let's take a look at some data that's been produced just recently from a number of expeditions. Again, this is taking samples and bringing them back on shore, but that still gives us a good idea of the kind of data throughput to be thinking about. For the Terra Oceans expedition, which was a great collaboration between lots of different folks in the EU, this is an example of, they basically looked at about 243 samples. That's about 1/100th of the number they collected. That generated about 7.2 terabytes of data. So you can multiply that by 100 and you're already up at about a petabyte from this single expedition. If you take a look at some work that we've been doing out at Station Aloha, basically we're doing some time series analysis to create a gene catalog for this particular ecosystem. And so just for my lab, in terms of working on this, and I won't go through all our workflow, but the bottom line is that this is about 1 terabyte of raw data and then 2 terabytes of basically data products from just a single lab trying to look at one project. So the amounts of data are going to be staggering, and I would say that the community is still working out how to effectively share data, how to effectively analyze it, and how to get standardization across different groups doing this. The Genome Standards Consortium has been doing a lot of work on standardization, so it's there. And as a final example, this is a cruise from last summer. One of the things we've been doing is try to map the biology and the physics and chemistry across these anticyclonic eddies, mesoscale eddies that move across the Pacific Ocean in our region. And so we had deployed a couple drogues. We followed those drogues with the Kilo Moana, and then took samples, 6 samples a day to get diel cycles across this whole sampling scheme. And so I think there are about 44 data points, but we were looking at a variety of different data types in each of those diel samplings. And so just in this one cruise, again, we've generated quite a bit of data. And that's just driving it a little bit too hard, but I just want to make the point that data handling will be an issue as we start to map microbial genome space on top of physical oceanographic space. So just a couple points to make. The need is obvious. We need to store, analyze, compare, and share these sorts of size data sets. And this is just kind of going through. If you think about the advances in the drop in prices, it isn't hard to imagine getting to petabyte size surveys even for single sites. It's going to happen. And the huge challenge is going to be handling, processing, interpreting, and visualizing all this data. And there's lots of folks working on that in a variety of contexts, from the human genome to environmental science. So if you have these on a vehicle, one way, I guess, to port the data would be to do it through an underwater cable. There are some folks thinking about that. In the water column, it's a little tougher because these are pretty big data sets, and some of the standard approaches for moving data around probably aren't practical. There are practical solutions, of course, to get around that, simply onboard hard drives and post-op data dumps. In fact, a lot of my colleagues, even working on land, are still almost mailing each other hard drives to exchange data. You can get around that. There's very good data exchange protocols where you don't have to do that. We heard a lot about potential Wi-Fi and hub-type approaches to move data around, and that's another solution. And again, cables are another approach. So Another challenge is how to analyze all this data, the rapidly growing data sets and needs for really high throughput sorts of analytical approaches, kind of pushing things to the cloud. That's pretty well developed actually in a lot of new platforms that use either virtual machines or containers that use the native operating systems are developing. And so I would call that as a problem that's beginning to be solved at this point in time. So just to kind of summarize the current and future trends in this sort of area that I see evolving and I think is going to be useful in a variety of contexts is that multi-platform data acquisition is going to become more and more common. And we've heard some examples of that earlier today. Real-time platform operational integration, we've heard about that. Biosensors are something that I didn't mention. A lot of folks are working on that. For our approaches, we're using samples and sequencing in the lab, but soon that'll happen in situ, I'm sure. And you know, data I/O is an issue if we do start generating data sets that large. Shore-based, I mentioned already, cloud storage and data sharing. These things are technically being resolved right now using these sorts of approaches for analytics. And one of our biggest challenges, and in fact some of the bottlenecks that we used to have even 3-4 years ago, have been solved by different algorithms that are able to allow us to compare the data much more quickly. So that's a constantly developing areas. And I think the data visualization, in particular what we already heard about today, how do we take the oceanographic context, all that data, and then combine it with some of the dynamic data from the microbial world and overlay that to get a better picture of how the physical, chemical, biological system operates as a whole. We haven't solved that problem, but it's an interesting one that I think a lot of smart young people will be trying to resolve in the near future. And with that, I think I'll close and would be happy to take any questions.
We have time for 1 or 2 questions before the break. Question?
Yeah, Greg Murphy from Maritime Alliance mentioned a couple times the kind of on the horizon DNA in-situ analysis. It's really the holy grail for public health, especially the sampling of the Enterococcus indicator species for beaches. What are the barriers to getting there, and is that the best option? Are there other alternatives, like modeling, for example?
Yeah, that's a great question. So I kind of have approached this from a very kind of fundamental kind of knowledge acquisition sort of approach. I don't think that's the way to go for particular targets. I think that for looking for specific targets that other kind of molecular-based methods, be they PCR or microarray technologies or other things on the horizon that are miniaturized, you know, the move is towards microfluidic solutions for a lot of these, is the way to go for particular topics, I mean, of public health concern. Those are in various states of evolution, both in the biomedical realm as well as in biotechnology. So I would say that the hurdles for those are more on the sensor end of things and sensitivity and determining thresholds for that. And certainly there's solutions that are coming forward in that front. And I couldn't even put a timeline on it. Chris is probably a better person to answer that question than I am. Yeah, so that wasn't a satisfactory answer, I know. But for the raw sequencing, for just taking a census of everything that's there, those technologies, I think, are just a couple years out. For really getting highly sensitive and, for instance, organisms that are there in very low abundance, so the signal-to-noise issues come in, and that's kind of target-specific development.
The last question before the break? No? Yes, sir.
Hi, Ed Hill from the National Oceanography Centre. People have been thinking about the future of the global ocean observing system, which at the moment is primarily physics climate orientated, but it is a globally distributed system, really tuned at looking at decadal basin scale variability for long-term change in the ocean.
Sure.
It's noticeably got very little biology or ecosystem variables in it, and this would seem to be the obvious way forward. But how would you characterize the challenge there of trying to have a globally distributed system for very sustained multi-decadal measurement? Is the data challenge you've described is already vast enough? Is there some other way in which we might be able to tackle this problem?
It's a good question, and I think, so we're not there yet. That's absolutely true. I would say that. But where I think things are headed, if you take a look at what Terra's done, what's happening in other parts of the world, is this: it's not an infinite number of genes in the gene catalog and marker organisms and sentinel species, if you will. That's actually getting mapped out right now, I think, in a fairly credible ways. And once that map is there, then it'll be very easy to more quickly use that kind of global database as a queryable entity that you are going to be able to more quickly query data sets. And to me, it's certainly something that should be done. We're trying to do it at Station Aloha right now. And I don't think that's too far off in terms of really looking at global microbial assemblages and how they're changing in a particular habitat like the pelagic ocean. So I agree, that should be done. I think we're not that far off. It does require some agreement about standards and data formats and that sort of thing. Those conversations are happening, so I think we're not that far.